This week's lab is focusing on the numerical methods, and we're contrasting that with the symmetry methods that we used. In the middle of this first section of the course, where we just looked at the symmetries of the wave function, and then the calculus week was the analytical methods. So we really have three methods to approach quantum mechanical problems. We'll use symmetry the rest of the semester for sure in dealing with full molecules. Whenever we do a Gaussian calculation, we're actually using the numerical methods. So I'm trying to kind of give you an idea of what Gaussian's doing. We're doing it in one dimension, Gaussian's doing it in three. We're doing it for a single particle, Gaussian's doing it for a whole molecule. So Gaussian is way more complex than what we're able to do in a spreadsheet. But it'll give you an idea at least of taking numerical derivatives, taking numerical integrals. Gaussian's doing all of that for us. This is the spreadsheet that I've retooled for you this year. I used to have you build the full-blown 15 quantum state, the box divided in 100 levels. But the thing was, it was such a big spreadsheet that if you were learning Excel at all, if you weren't very good at it, you just got lost in the sheer number of wave functions. And so I cut it back to 2 wave functions. And I've built the spreadsheet without any of the guts. So the framework's there, the skeleton's there, and you're going to actually just fill in the wave functions and do the derivatives and do the integrals yourself, but at least you'll know exactly where everything goes. So this is the example. This is what you're going to download from Blackboard. It's the student version of the workbook, and you see it has the wave function labels here, but there's no wave functions. And so you'll take this formula here and you'll enter in the Excel version of that formula, copy it down, and learn about anchoring. And we talked a little bit about that last time. There's also on the YouTube channel some Excel bootcamp videos that if you're at all struggling with Excel, this is worth doing. Let me try to find this. Let's see. PChem at SAM. There we are. And playlists. And here's Excel Bootcamp. And so it talks a lot about this anchoring cells, some charting pro tips, some things with transpose and NIM-MULT. And that's pretty much it. There's only about 4 videos on the Excel Bootcamp. I ran out of time. I was doing it in August last year, and then school started. So. But I got most of the skills we need for this course are in that Excel Bootcamp. And so then we'll talk about the centered derivatives a little bit more today with some graphical examples, and then the integration. But today's lecture is mostly focused on this last piece of your spreadsheet. You get through calculating the energies of the wave functions, the transition dipole moment integral, you calculate those, and you'll have this little 2x2 matrix that has the transition dipole moment. You'll change these little 1s and 2s, these quantum states here, to determine the selection rules. And so if you wanted to see if a 3 to 4 transition was allowed, then you can type a 3 and a 4 in those yellow boxes, and we'll calculate the transition dipole moment for 3 to 4. If you want to go 1 to 3, that's a delta n of 2, is probably not going to be allowed. Well, you can test that. You can put 1 in there and 3, and then look at the transition dipole moment integral result. So it's really a lot faster than doing it by the analytical method. You can just type in 2 numbers and hit enter, and then you get the integral. So that's really great. Now, it should be 0, but with rounding errors, it might come out to be like 10 to the minus 33. That's essentially 0. So when something's allowed, it might be 10 to the minus 4, 10 to the minus 5. That's getting up there to the 5th decimal place. So that I would consider a loud transition. That might be an overtone. But when it gets down to 10 to the minus 17 or higher, 10 to the minus 20, those are essentially 0 for Excel. And then this last piece is what we're going to focus on today, the simulation of the spectrum. So plotting the simulated spectrum of the transition, you only have 2 quantum states, and so you can really, in this spreadsheet, only calculate 1 peak. So you can calculate the difference between two energy levels, and that difference between 2 levels is the spectral line. It tells you where in the spectrum it's going to be, and the transition dipole moment integral tells you how tall that peak will be. And then the Gaussian will give you the line shape, how wide the peak is. So you have the height, you have the width, you have the center of the peak from the difference in levels, and so you can calculate the location and the shape of that peak. Today we're going to talk about the bigger spreadsheet where we do, I think it's like 35 or 40 different peaks in the spectrum. And so I'll show you how that's constructed. And then you'll have that full-blown spectral simulation workbook that you can use in the next lab to simulate your spectrum of the infrared and Raman spectra of benzene or chlorobenzene. So let's dive in. So what do we need for spectral simulation? We need a calculation of the energy levels so that we can take differences between those. Because light causes one quantum state to jump to another. And so we need to know where the levels are first, and then we need to know the intensities or the probability of making that jump. So in spectral simulation, we need some way to know the selection rules and the energy levels. Gaussian can do that for us. Now in our particle in a box, we're going to do it in the spreadsheet, calculating the Schrodinger equation, calculating the transition dipole moment integral. But next week in the infrared lab, Gaussian's going to give you, or it already has, you've done the calculation, the frequency calculation on benzene, the frequency calculation on chlorobenzene, and so Gaussian will list all those frequencies and all those infrared intensities. So everything we did for the particle in a box, the transition dipole moment, all of that is done for you in Gaussian. And the results are the vibrational frequencies and the vibrational IR intensities. And so you can type those into this spreadsheet and get the simulated spectrum. So what I've created for you that puts a Gaussian line shape on every one of those transitions, you won't mess with any of that. All you'll do is type in the new frequencies and the new infrared intensities, and down at the bottom you'll have a simulated spectrum in the infrared. So let's see what goes into that. So we do the Schrodinger equation to get the wave functions and the energy equation, and then once we have the energy equation, we can calculate the selection rules using the transition moment integrals. This will give us the intensities. So let's look at the Schrodinger equation first. We have the wave functions, and notice that you're calculating 2 of them. I've calculated 15. It goes on beyond the screen. And I've plotted just the first 4. Get used to seeing these wave function plots. You see, let's see, that's nice. It's not shown on here which one is which. So which is the ground state? What color? Good. How do you know that so fast? Yeah, 0 nodes. It's just one lobe, 0 nodes. And so then what's the n equals 1 or n equals 2 state? It's the red one, because it goes up and then comes through 0 here, goes down and comes back. So it just has 1 node. The one with 2 nodes would be n equals 3. The one with 3 nodes would be n equals 4. So those are our first 4 wave functions. I could have plotted all 15, but it would just be a smear. You wouldn't really be able to tell the difference between them. And so this was solving the Schrodinger equation as the second derivative of that wave function, left multiplied by the wave function and integrated over all space. And so how do we take this derivative? I keep talking about center derivatives because we want to keep the symmetry of the wave function unchanged. There's 3 ways to do it. You could see if I'm sitting at 0, I could calculate the forward derivative, which means this point minus that point. So the rise over run. The y value is less than this y value. And so let me do it with a pen so we can see it on the screen, on the video. So if I'm sitting at x equals 0 and I look forward and calculate delta y, it's a negative delta y, it's a positive delta x, so I'll have a negative slope. But I'm sitting at 0, so that's really not accurate. If I'm sitting at 0, I have a slope of 0. But if I calculate the difference forward, I have a negative slope, and that's a problem. What if I calculate the point behind me? Then I have a positive slope, it's not 0. And so the forward slope is going to be inaccurate. The backward slope is going to be accurate. So we do this centered slope. So I take the point in front of me and subtract the point behind me. And then I plot it right there on 0. So that's the centered derivative. So maybe that's the best way to show it, is this graphical method of showing you that the forward slope's inaccurate, the backward slope's inaccurate, but the centered slope maintains the symmetry. So at point 0, x equals 0, you have a 0 slope. Now here's the first derivative of the wave function, and you see that the wave function was a sine function, and so the derivative of sine is cosine, and we see that these start out at a maximum at the left of the box, and so they look cosine-like. Now the amplitudes are starting to change. The higher quantum states are having now a constant times that cosine function, and so the amplitudes are starting to grow as we take the derivatives, because the things that are inside the sine function, when they come out, they're constants and they're multiplied by that cosine function, so that the amplitudes are growing of these waves. Psi double prime, now we're back to sine, minus sine, so we see the n equals 1 state is now going down. See that? So we have the minus sign, and then also we see that the amplitudes are growing. Remember, the Schrodinger equation has this eigenvalue, eigenfunction nature. So we're going to take the second derivative of this wave function, and then we're going to get that wave function back times these constants, and that's where the energy is. So this is telling us that the kinetic energy is related to the curvature of the wave function. The second derivative is the curvature. And so if the curvature is larger, it has a larger energy. One way to get higher curvature graphically is something that has a large amplitude that still goes through 0. And so we can see the energy in the amplitude of these waves after we take the second derivative. You see, this ground state has a pretty small amplitude. First excited state quite large, and it gets bigger and bigger as we go. So we're actually seeing the Schrodinger equation graphically. As the amplitudes grow, we're seeing the higher energies of those excited states. So to get this in Excel, we have these matrix multiplications. We have a 15 by 100 matrix in the HD sheet that I have. It says DW's HD version of your workbook. And so it has 100 marks across the box, so 100 different rows, and 15 wave functions. And so it's quite a large matrix, a 15 by 100 matrix. We turn it sideways so that when we multiply by the wave functions, actually the second derivatives of those wave functions, then we get a 15 by 15 matrix that contains the energies. And so this is the matrix here. So we see those diagonal elements are the energies for our wave functions. And that's another thing that you'll see in a matrix form of this eigenvalue, eigenvector equation, that the diagonal elements are the eigenvalues. So you'll hear me use it interchangeably. Energies, eigenvalues, diagonal elements, those are all the same thing for the Schrodinger equation. And so the simulation process, we now have the energies. We're going to use the transition moment integral to get the intensities. We can use x as our representing light for absorption and emission, x squared for Raman and Rayleigh scattering. And those selection rules will be evident from the matrix that we have. So this would be light perturbing the first 4 wave functions. So if you multiply the x-axis, because it's representing that dipole, that electric dipole in light, multiply that by the wave functions. I'm designating that in the titles of the columns by x psi, so it's x times psi. So x times the wave function, and here's what we have. So this blue function is still the first quantum state, n equals 1, but it's been multiplied by the x-axis. And so that pins it to 0 in the middle, because x is 0 in the middle. So all of these go to 0 in the middle because x is equal to 0. So then the left side of that ground state wave function became negative because it was multiplied by negative x, and then the right side got larger because it's multiplied by a number that's greater than 1. And so notice how that this blue curve now resembles the first excited state. And so it's compatible, if you will, with that first excited state. So when you do the multiplication and integrate over all space, you're going to get a non-zero transition moment integral. So it makes the symmetry work out with the excited state, and you get a non-zero integral. And so these transition dipole moment integrals can be done in one step with this matrix multiplication. So you have the transpose of the wave functions times the x psi, or the light perturbed wave functions, and that m mult will give you an integral over all space, and then times dx. So you have a 15 by 100 matrix times a 100 by 15 matrix, and the outer elements, the 15 rows and 15 columns, makes a square 15 by 15 result matrix. And so this is the intensity or the transition dipole moment integral for the absorbance, and it's all 15 transitions to all of the other 15 states that are possible. So this is 225 integrals done with just 3 keystrokes, Control Shift Enter. So that's fantastic. So this is what we see with the transition dipole moment result matrix. And so the integrals are 0 when you have a change in 2, 4, 6, etc. And so what I mean by that, if we sit here at state 1, and we look over here, if I add 2 to 1, I get 3, and it's 0. All right. If I add 4 to 1, I get 5, and it's 0. If I add 6 to 1, I get 7, and it's 0 too. Trust me, it's behind the little box. Okay. And you can see that all the way across the whole table. So this pattern here is telling us our selection rules. The integrals that are not 0 are the ones where there's a delta n equals 1, 3, and 5. So all of the odd jumps. And so we can, we'll see those patterns. Let me skip ahead just to show you those patterns. Well, I don't know. I thought it was... But you see that these large intensity values, notice these large intensity values here are the delta n plus or minus 1. So what's a plus or minus? Well, this would be, let's say these are the lower states, so 1 to 2, that's a plus 1, but 2 to 1 is a minus 1. So they're equal intensity. This is another interesting result. This tells us, I mean, Einstein got a whole paper based on this. He did the statistics of absorption and emission and proved that they're the same. That the probability of absorbing light with a photon, you know, assuming equal populations, light coming in, hitting a molecule, and having it absorb is the same probability as stimulated emission, light coming in and hitting a particle and having it emit a companion photon. And we've proved this with the particle in a box. So this is pretty cool, that we have the same transition probability of absorption and stimulated emission. These are overtones. So delta n of 3, so 1 to 4, or 4 to 1, also the same intensity or probability. Let's see, can I change the pen? Yeah, I can. So this diagonal element here is the plus or minus 3. And this diagonal element here, plus or minus 5. And they just get less and less probable. And so way out on the wings, I mean, these are showing zeros just because they're less than 0.00, less than 0.005 or 0.05 because they would round up. And so they're just being truncated. But you get out here, and if you were to increase the decimal places, it might be 0.003 or something like that. Now, the definition of those selection rules are all the allowed transitions. So the non-zero elements are the selection rules. Let's count how many people we have. 5, 10, 15, 20. Okay, everybody's here. So I'm going to go around just for my sake and take a break here. And I want to go just up and down the aisles, and this is just for my own personal benefit. I'm going to video you. Just say your name so I can get a name and a face, and I can look back at that and kind of learn names. So just take a little break here. And yeah, so I normally did this with like photographs, and in Excel or in PowerPoint I would put your name by your face, but it took like several hours, whereas a video is much faster. So I'm just gonna go up and down the aisle, and I'm gonna say your name like how you want to be called. Okay, so we'll just do this. This is not for Facebook or anything. This is for my own personal use. So don't worry. You're like, I didn't do my hair today. Yes.
Kyle Brennan. Kyler Kelly.
He would take pictures of his student with his camera, like he keep these photos or whatever. And one of the best things he likes to do is he likes to is an English class, so you gotta dress up. And so he makes people break.
Thank you so much. I really want to learn your names, and I was counting. I was kind of waiting for the day when everybody was here, and I'm happy. Good old Monday, y'all are here, everybody. All right. All right, so now we'll continue on, and what we're going to do now, we have the selection rules, we have the energy levels, we have sort of the intensity probabilities between the levels, which give us the spectral lines. We need to calculate where those lines are going to be in the spectrum. So since we have the levels, we need to calculate the transition equations. Remember doing that? So here's a bit of a review. So the delta n equals plus or minus 1 transition equation. This is what I was looking for on the test, to show it algebraically. So not to put numbers in, but just to show it algebraically. So you can look up there and see we're putting in e of n plus 1 and subtracting e of n. So wherever there's an n in the energy equation, we put n plus 1. Wherever there's an n, so we have that difference. So that's the energy differences for all the n plus 1 transitions. And so we can simplify that algebraically. We pull this constant out front, h squared over 8ml squared. We'll just leave that as a constant because it just appears all the time in all of these different things. We'll even maybe pull a 2 out. So we have 2 times this constant times m plus a half. And that plus a half, that's our 0-point energy. You know, it has nothing to do with syndrome, you know, and his gloves. Any Incredibles fans? Anyway, that's what he says. I'm using 0-point energy. I'm like, man, I wish I could get 0-point energy to do that. I could levitate things. Anyway, it's fun when you see these scientific terms show up in popular movies, but they're never actually used accurately. So here's for the overtone, n plus 3 overtone. So wherever there's an n, we put n plus 3, do the difference, algebraically simplify it. We see that same constant, h squared over 8ml squared, but now we have a factor of 6 times that constant. It goes up, it's linear in n, but with a different slope. So these peaks will jump. They'll be further spaced. They'll be spaced by 6 times this constant. The fundamental and the n equals 1, delta n equals 1 would be spaced by 2 times this constant. And so now we have our transitions. We know where those spectral lines are going to be in the spectrum. We need to know if there's going to be actually any molecules in there for the hot bands. And so for anything that originates in n equals 2 or higher, we need to calculate the thermal population. We don't have to do this if we're just modeling the fundamental. So when we get our benzene spectra and our chlorobenzene spectra, we don't have to calculate the Boltzmann distribution because we're just doing the fundamentals of every vibrational transition. Those vibrations are in the hundreds to thousands of wave numbers, like 400 to 4,000 wave numbers. And room temperature is really only about 200 wave numbers. So we're not going to have thermal excitation of those levels. So we're just not going to see hot bands in the room temperature infrared. So we wouldn't have to calculate them. But for our particular spectrum, we'd like to calculate the hot bands because we really want the spectrum to be interesting. So we're putting in a huge temperature. That's why you'll model, or you'll see on my spreadsheet, it's modeled at 500,000 Kelvin, because I want a lot of hot bands and I want to make the spectrum look interesting. And so this Boltzmann equation is here. It's the degeneracy of the level, which none of our particle in a box energy levels are degenerate, but we might have that in other situations like rotation. And so G of n is 1 for all of these. E sub n is the energy equation for the particle in a box. Here's KT. So this is the only place temperature comes into play. Notice we've never really talked about temperature in our particle in a box, because temperature is not in the wave function. Temperature is not in the Schrodinger equation. Temperature is not in the transition dipole moment integral. So that's a great exam question. Tell me what depends upon temperature. Right? Is it the wave functions? I mean, you can think through, when have you ever seen capital T in any of these equations? Not until you get to the Boltzmann distribution do you find temperature. And it tells you really if you're going to have hot bands or not. The fundamental will really be unchanged. But you have to add a lot of thermal excitation to start to get hot bands. Or if you want emission spectra, you have to have molecules in the excited state before they can emit. So this is showing you the probability of being in those energy levels relative to the ground state. So these are relative probabilities. They don't sum to 1. If they were true probabilities, they would all add up to 1. Okay? But you can see that they're relative to the ground state because this says it's calculated based upon the lower quantum number. So it's this one right here, 1, 2, 3, 4, 5. So this third row is the E sub n that we're using. And so the probability or Boltzmann factor for being in that ground state is 1. Well, if these were true probabilities, then everything would be in the ground state and all the others would have to be 0. If they sum to 1 and the first one's 1, everything else has to be 0. But the next one's 9.5. So now we're up to 1.95. You know this isn't true probabilities because they go past 1. But these are all relative to the ground state. So this has a 95% chance relative to the ground state of being populated, because we're at a really high temperature for this molecule. I think we're at 500,000 Kelvin. 87% chance of being in the second excited state, n equals 3, and then you see it starts to drop off. So our absorption profile is going to be BIG. I had to come up with a great acronym. Go big or go home, right? So you got absorption, B is Boltzmann factor, I is that transition dipole moment integral, so I is integral, and G is Gaussian, or the line shape function. So Boltzmann times integral times Gaussian, that gives you a peak in the spectrum. And so this A stick, that A stick is this sort of the stick spectrum, and the stick spectrum has just the B and the I, the Boltzmann times the integral. And that gives us a stick. It doesn't give us the line shape. We'll do the line shape next. But you could plot just a stick spectrum, and you've seen those plots already. So the stick spectra are right here. You see how they're just vertical lines? So stick spectrum is pretty easy to calculate. You don't need to know the instrumental line width or the Gaussian. You don't have to pick a line shape function. You just need the Boltzmann distribution and the transition moment integrals. And you need the transition equation to tell you where the peaks are on the x-axis. So here's the based upon energy. These are all of the hot bands. That very first peak is the fundamental. Y'all did really well on this in the previous exam, so this is a bit of review. I've labeled all the quantum states, so just make sure you review this, because this is something that we will see throughout the whole semester. Not this exact plot, but this concept of fundamental, hot bands, overtones. And so then next we will add in, if you wanted to plot this by wave number or wavelength, and this is going to be something you'll have to figure out. You have the transition energy, converting that to wavelength is a unit's nightmare. Okay, so this week I haven't calculated that, and I haven't shown you how to do that. You've just got to figure that out. Yeah, so what's new? Yeah, C over lambda. So that's a key piece of the puzzle. Okay. So plotting this versus wavelength, notice the equal energy spacing now is unequal because energy and wavelength are inversely proportional. So you have the fundamental separated over here on the right. That's the shortest energy jump. So that's the longest wavelength. And then the wavelengths get shorter and shorter as the energy levels get further and further apart. So all of these, starting here, going to the left, are hot bands in the blue. Now there'll be one overtone that starts in the ground state, but then the others are both hot bands and overtones. So that first overtone is just a pure overtone, and then you have hot band overtones. And so now we're at the last piece of the puzzle for simulating a spectrum, putting a line shape function on all of these transitions. And so this comes from our apparatus, how narrow our slits are, how good our monochromator is, how it disperses light. But it has to do with nature too. If you've got a gas phase spectrum and some of the molecules are coming towards your source and others are going away from your source, you're going to have red and blue shifts of the frequencies. And so even if you sent a pure frequency at that molecule, if the molecule's moving, you're going to have velocity changes. You'll have the Doppler effect, and the Doppler effect is a Gaussian line shape. So even if you had a pure single frequency laser, you'd still have Doppler broadening due to the motion of the molecules. You might have collisional broadening. So your energy levels for a molecule isolated in space are sort of perfectly separated, but if during the experiment another molecule happens to be hitting that molecule at that same time, that's going to shift the energy levels a little bit because they're going to interact with each other. So there's a lot of natural effects. There's collisional broadening, Doppler broadening. There's the uncertainty principle. So you have a lot of natural effects and then you have a lot of instrumental effects. Most of the time, the instrumental effects are larger than the natural effects. And so we don't see necessarily the Doppler broadening or the natural line shape or collisional broadening in our instruments. Those will be for really high resolution instruments. Most of the time, you just have the instruments, slits and monochromators that are limiting you, and that gives you a Gaussian line shape. So Gaussian line shape is the easiest and most applicable to most instruments. When you have super high resolution instruments, you might have another line shape function. So let's go through 3 of the main line shape functions that you'll have. And I'll be sure to tell you really what I want you to take home from these. I do not want you to have to commit these to memory because I don't have them committed to memory. I can't just spit out these functions. I could probably do the Gaussian, but I couldn't give you the Lorentzian or the log normal function from memory. Here's the resource where I got these functions. What you have is a center wavelength, and that's given by your transition equation. So go ahead and write that down. The center wavelength comes from the transition equation. I'll repeat. The center wavelength comes from the transition equation. That was that E with n plus 1 minus E of n. That was that delta. That's the difference in energy levels. That center wavelength is also what we call the spectral line. So that spectral line is centered on that center wavelength. The peak height, it's labeled up here. The peak height is that transition moment integral. It's proportional to it, okay? It's the integral squared. So the peak height is related to the transition moment integral squared. And then the third piece is that line width, how wide your peak is. That depends upon the experiment. The line width depends upon the experiment. So this is when it gets real. When you actually go to the lab, you'll have peaks that have widths. And this piece will really help you understand the instrumental if you're in instrumental. Let's look at a different line shape function. Oh, first of all, what do you notice about the features of this curve? Notice it's symmetric. That's a very important piece. That the Gaussian shape is symmetric, meaning that the very middle of the peak is the center wavelength. The peak maximum is the center wavelength. So you could find the peak maximum, and that's the center wavelength. Okay, let's look at another one. This is the Lorentzian line shape. Same situation. The center wavelength is that transition comes from the transition equation. The peak height comes from the transition moment integral. But the line shape, also line width, comes from the experiment. But notice it has a different shape to it. It's not a Gaussian. Let me go back. Here's the Gaussian. Here's the Lorentzian. The Gaussian, Lorentzian. What do you notice about the peak? Pardon?
Can you go back one?
Here's the Gaussian.
That one starts at 0, or it starts, this one starts higher.
Oh, you say over here on the left? Yeah. And these have very similar widths in the middle. So how do you decide where to draw the width? Right? It's a good question. Where do we draw the width? This is an important spectroscopic term. FWHM. That's how you decide where to judge the width of a peak. Can you figure out what it means? Full width HM. What do you think HM stands for?
High.
Something with height, or this is half. So full width, half M. Look up there what we've got. Where did I draw my double-headed arrow?
Middle.
Half what? Half maximum. So the full width at half max. Very, very important spectroscopic term, full width at half maximum, because that's how you decide how to draw the width of a peak. And so if we look at the Lorentzian, it has essentially the same full width at half maximum as the Gaussian, but down below that, it gets fat. Okay? So here, see they have the same FWHM, but the Gaussian falls off and goes to 0 faster than the Lorentzian does. Okay. And so it's sort of like if you're standing here with your toes pointing out. I really can't get this on the video, but the Lorentzian has bigger feet, right? Because down there past the width, it's really big, down by the feet. And so we call these outer parts of a peak, we call those feet. And Lorentz has bigger feet than Gauss. Okay. I don't know if in reality Lorentz had big feet, but his curve, the one named after him, has big feet. Okay. And so then we have the Voight, which is a combination of the Gaussian and the Lorentzian. So it's sort of a percentage, like maybe 50% of each, or 20/80. And so this is when you're doing an experiment that's pretty high resolution and you start to see big feet on your peaks. You're like, wait a minute, I'm starting to see, because the Lorentzian line shape is more related to nature. So the natural line shape is the Lorentzian line shape. And so if you get a high enough resolution spectrometer and you start doing high resolution studies, you might start to see that your peaks look less and less Gaussian. Now you may not have the highest resolution, so you may not actually see the Lorentzian line shape perfectly, but you might start to see some percentage of the Lorentzian line shape. And so the Voight profile allows you to add in like 20% Lorentzian and mix that with your Gaussians and get a really nice profile. Now, why on earth would we be that specific as to mix in 20% of a Lorentzian? You know, one way to measure where that center wavelength is just to pick the maximum of the peak. But what if there's a little bit of noise up there and you end up picking the wrong data point, like one that's not the maximum is actually higher just because of noise? You're basing your whole analysis on one data point. But in your spectrometer, look how many data points you have. You have the whole curve. Why not use all of them? Right? If you're trying to find the center wavelength and that's your unknown, and you pick one data point, you have one equation and one unknown, and really not very good statistics in that situation. But if you pick every point on the curve, you've got 100 measurements and one unknown. You will know the wavelength very well if you model the whole curve. And so that's what scientists will do if they're really into spectroscopy and trying to nail down these locations of these peaks, is they'll model the whole curve. And in order to get that to fit well, they need to model the line shape. They need to actually mix in 20% Lorentzian and 80% Gaussian if that's what they're starting to see in experiment. And both of those peaks will have the same center wavelength. And so they'll get, again, a very good measurement of that center wavelength. The last one we'll cover is the only one that's asymmetric. So notice all of these have, that center line has been right in the center of the peak. But the log normal line shape is asymmetric. Look at that thing. It's strange. Okay. This one's actually tailing to the left. This is a skewed curve. So in statistics, you have skewness. It tails to low or high values. In this case, in wavelength, it's tailing to low wavelength, and so we would call that a negative skew. It could tail the other way as well. And so this has this asymmetry parameter right here, this rho, Greek character rho. It's present in this formula in several places, but this is the asymmetry parameter. And it's this high minus the center wavelength divided by the center wavelength minus low. And so if this is less than 1, then the denominator is big. And so you see here, this piece right there is the denominator. And this piece over on this side is the numerator. And so if the asymmetry parameter is less than 1, it will tail to low values. If the asymmetry parameter is greater than 1, it will tail to high values. So I could make this peak tail to the right by having a row that's higher than 1, or I could make it tail to the left with a row that's less than 1. The one thing I can't do in this function is have rho be 1. Then the function blows up because we're dividing by, we're taking the log of rho right here. And so the log of rho is 0, 0 squared is 0, and 0 is in the denominator. So you can get close to 1. You can do 0.99999 and it'll be fine. But if you type in 1 for rho, it blows up. Okay. So this is very useful in modeling UV vis spectra because a lot of the peaks in the UV vis experiment are asymmetric. And so if you wanted to make a realistic looking spectrum in the visible range, you would need to use a log normal peak. And you would need to match that asymmetry parameter so it matches your spectrum. Now, one way that I've used this in modeling visible spectra accurately is to get the colors of compounds. And so in our RGB lab, we will actually calculate the colors, we'll measure the colors of substances and calculate their red, green, blue values. And then I wrote a part 2 paper. I don't have y'all do this part, but in the part 2 paper of that, we actually use a Gaussian calculation, put a log normal function on there, and calculate the colors of molecules. So you just build the molecule in Gaussian and then run it through this spreadsheet and you know what color it is. And that's pretty cool. So this line shape function in Excel, this is the last piece, is in all of these columns. You have one of these columns in your little, in the student workbook, but we have a bunch. Not just 15, but all the allowed transitions, so more than 15. And so these over here are individual peaks for every transition. And then this, over here, this, come on. So each one of these has a Gaussian line shape, a height, and a center wavelength. And then the composite spectrum is the sum of all of those. Because the instrument doesn't know. It sends a wavelength of light through your sample. And if one is an overtone and another is a hot band, all the spectrometer knows is that there's light missing on the other side. Okay. And so in Excel, you just have this summing across all of those peaks. And at every wavelength, it's getting the contribution of every peak that could absorb there. And with that, you get this spectrum. So if I'm sitting at this wavelength, I'm getting the absorption of all of those possible transitions. And it's adding up to that value. Over here, I just have one peak that's contributing. But over here, I have a bunch of peaks that are contributing. And that's why even though these are tiny, you add up the contribution of all of those hot bands and overtones, and the spectrum, composite spectrum, is up here. Huge absorption value. And so that's how you simulate spectrum. You need to know the transition equation, the selection rules, the transition moment integrals, and then an instrumental line shape. And that's it.